Hi, in this video lecture, we're going to talk about the Laplace transform. Laplace transforms are powerful tools in solving linear ODEs or ordinary differential equations and related initial value problems, as well as systems of linear ODEs. Some of its applications can be found in electrical networks, springs, signal processing, and other areas of engineering. Let's have the integral definition of the Laplace transform. So given a function f of t, the Laplace transform, which is a function of s, is obtained by evaluating the following integral operator. So given f of t, we take the Laplace transform. This is the operator, the Laplace operator. We multiply f of t by e to the negative st. Integrate with respect to t from 0 to positive infinity. The output will be a function of s. So note that f of t is defined only for t greater than or equal to 0, and we assume that this improper integral exists. Let's find the transform of e to the at for t greater than or equal to 0. So we're going to use the definition of Laplace. Okay. So Laplace of e to the at. So using the integral, we multiply the function by e to the negative st. Okay, dt from 0 to positive infinity. So to integrate, we combine the exponents, try to factor out t and then the negative sign to get negative of the quantity s minus a multiplied by t. So this will take integral e to the u du over u will be negative s minus a times t. So our derivative is negative of the quantity s minus a. So reciprocal of this will be your integrating factor. Now since this is improper, so we take the limit. Okay, let's introduce a variable here as k approaches infinity. Now the integral is negative 1 over s minus a. This is the correction factor. Integral of e to the u is e to the u. So just copy. Okay, so this will be from 0 to k, no? As the limit of k approaches infinity. And then we substitute the limits, okay? So we factor out this constant. So e to the negative s minus a k minus this is e to the 0, no? When t is equal to 0, everything will be 0. So this is equal to 1. Now take note that if k is infinity or k approaches infinity, so you get you get e to the negative infinity. which is actually equal to 0, no? E to the negative infinity. That's 1 over e to the infinity. E to the infinity is infinity, and 1 over infinity is 0. So this is 0. And finally, we get 1 over s minus a. So we have a restriction, of course, that s should be greater than a, no? So the transform of e to the 80 is equal to 1 over s minus a. Now, we can avoid the integral definition, no? By using the Laplace transform table. So this summarizes the transform of some basic functions. Okay, the transform of 1 is 1 over s. T to the n is n factorial over s raised to n plus 1 when n is 1, 2, 3, and so on. So t and t squared will follow this formula, no? Now, if a is not an integer, okay, then we can apply the gamma function. Gamma of a plus 1 over s raised to a plus 1. And then, this is what we obtained a while ago. E to the 80 is 1 over s minus a. And then, this is for the cosine function, sine function. For hyperbolic, we just replace the positive sign here by negative. Now, these two can be obtained using the properties, no, or Laplace transform, the translation theorem. Okay, so I'm not going to discuss the definition of gamma, which is also in the improper integral form, no? So we just focus on the properties. Gamma of n plus 1 is n factorial, where if n is an integer, gamma of 1 is 1, gamma of n plus 1 is n gamma of n. This applies for n greater than negative 1. And gamma of 1/2 is square root of pi. This is square root of pi, sorry. So, this has to be square root of pi. So, there is a correction here, no? Okay, so find the Laplace transform of the following functions. So, we will use the Laplace transform table. Okay. So, from the table, the e to the 80 is 1 over s minus a. So, in this case, we'll take a to be negative 2. So, the Laplace transform of 2/3 e to the negative 2t. Okay, so factor out. Just place the constant before the operator. Apply the formula. So 1 over s minus 2 will give you 2 over 3 s plus 2. So this is your Laplace transform. Of course, s should be greater than negative 2. And for t to the 5th, so this will follow the formula since n is 5, so that's an integer. So we follow the formula that is n factorial over s raised to n plus 1. So the Laplace transform of t to the 5th, therefore, is equal to 5 factorial over s raised to 5 plus 1. 5 factorial is 120. Okay, so this is s to the 6. Okay, of course, s should be greater than 0. Okay, let's have the next slide. Note that the Laplace transform is a linear, this is a linear operator. So this is a linear operator. So what do you mean by linear, no? linear operator, we can, if we get the transform of the sum, just like the derivative, you can distribute the operator. So this is just Laplace of t to the 3 halves plus Laplace of e to the pi t plus Laplace of 8 sine 2t. Sorry. Okay. Now here we apply the gamma function because 3 halves is not an integer. So your a here is 3 halves. Okay, so this is gamma. Applying the formula, you have gamma of a plus 1. So 3 halves plus 1 over s raised to n plus 1, or 3 halves plus 1. And then, we may continue. So plus, this is plus e to the pi t is 1 over s minus pi plus constant. Okay, and then your a here, or sine 80, the Laplace transform is a over s squared plus a squared. So 2 over s squared plus 2 squared. Okay, but how do we simplify gamma of 3 halves plus 1? Okay, so I'll put it here. Gamma of 3 halves plus 1 is 3 halves. Gamma of 3 halves. 3 halves can be expressed as 1 half plus 1. And then applying the property that gamma of n plus 1 is n gamma of n. N gamma of n. So we have 3 halves times 1 half gamma of 1 half. So this is 3/4 square root of pi, which is your gamma of 1 half. So therefore here we have 3 over 4. Square root of pi times 1 over s raised to 5 halves. Plus 1 over s minus pi plus 16 over s squared plus 4. So you don't need to simplify this as one fraction also, as you can leave this as your final answer, or consider this as your final answer. Now for the last example, we don't have a formula that will give you the Laplace transform of cosine squared, but note that we can simplify this. We can simplify this into 1 half plus 1 half, and then cosine of 2 square root of 3 multiplied by t. Applying the double angle identity. So 1 half cosine squared theta is 1 half plus 1 half cosine 2 theta. This is our theta, so multiplied by 2. And then we have a direct formula in getting the transform of the following. So for a constant, that is 1 half times the Laplace transform of 1 is 1 over s. So you have here 1 over 2s. And then 1 half here. The transform of cosine function is s over s squared over s over s squared plus a squared. So we'll take this as your a. So we have s here over s squared plus the square of this, which is 2 square root of 3 quantity squared. Okay, or we have 1 over 2s, okay, plus s over 2 s squared plus, what is the value here? You get square root of 3 square is 2, rather 3 times 4, you get 12. So I get 12 here. 3 times 2 squared, 4. Okay. So this is your final answer. Okay. Let's have the next slide. The unit step function. In engineering, functions that are either off or on are usually encountered. No? The one important example of these functions is the one occurring in electrical systems, particularly on the impressed voltage on a circuit that can be turned off after a period of time. That said function is known as delayed unit step function for c greater than or equal to 0. This function delays its output at the value 0, which is the off function, until a certain time, t equals c, and then assumes a constant value, 1 unit, which is the on function. Okay, so this is the unit step function. This is just a symbol, u of t minus c. Okay, see here, referring to the constant here in this graph. So it's either 0 or 1. So consider a value c. Okay, so if it's for t equals c, or for t greater than c, the value of for t less than c, the value of the unit step function, so this is your dependent variable, is 0. So the graph will be along the t-axis. The independent variable here is t, and then 1. So this is your u equals 1 for t greater than or equal to 0. So this is open, this one is closed. So this is the graph of your unit step function. And then the unit step function is also known as the Heaviside's unit step function. Now, if you apply the integral definition, okay, you can verify that the transform of this, okay, will be e to the negative cs over s, no? for s greater than 0. Okay. So express the given function in terms of the unit step function and find the Laplace transform. Okay, so we first express this in terms of the unit step function. Okay, okay, so from the definition, so we'll take this as c equals 5, no, or 5 here will be taken as c. So for t less than 5, the value here must be equal to 0, so you can okay, so if you want this to be 0, then you add negative 2 plus this form of the function. So 0 for t less than 5. Okay. And then what happens here? So when you add negative 2 here, so that will be, you add negative 2, so add positive 2 here. So when you add negative 2 to positive 2, you get the original function. So this is for t greater than or equal to 5. Okay? And then this has to be equal to 1 in the unit step function. So you have negative 2 here, and then we factor out 6. Okay, so 6 times 0, you still get 0. So for t less than 5. And then this is now equal to 1. So 6 times 1, you get 6 here. Okay? So when you try to simplify this function, you will get the original one. So we just want this to be in terms of the unit step function. So this is now u of, this one is the unit step function, u of t minus 5. So the Laplace transform of f of t, okay, will be the Laplace transform of negative 2 plus 6 Laplace transform of the unit step function. Okay, so this is negative 2 over s plus 6, okay, e to the negative, okay, negative 5. The formula is e to the negative cs over s, no, for u of t minus c. So your c here is, your c here is 5. Okay, so this is negative 5s. So for the final answer, this is negative 2 over s plus 6 e to the negative 5s. So this is your final answer. Now you can solve this using the integral definition. So how are you going to do that? Okay, so this is the Laplace transform of f of t. This is a discontinuous function. So note that your integral is defined only from 0 to positive infinity. So this is from 0 to positive 5. No? So for this interval from 0 to 5, your f of t is negative 2. So e to the negative st times negative 2 dt. Okay, plus this is 5 to positive infinity. The function is 4. So e to the negative st times your f of t in this, for this interval, is 4. So you can integrate. Okay, so this will be negative 2 times, you have a correction factor of negative 1 over s e to the u, okay, from 0 to 5, plus you have here 4 times negative 1 over s e to the u, e to the negative st, from 5 to positive infinity. So this is 2 over s e to the negative st when, okay, So I can factor this out 2 over s. And then your t is 5 here, so 5s. And then e to the 0 minus e to the 0. So this is equal to 1. Minus 4 over s, so factor that out. So e to the negative infinity will give you 0 here. Minus e to the negative 5s. Okay? So what happens here? We now have 2 over s e to the negative, okay, e to the negative 5s minus 2 over s, okay, this is 1, this is 0, and here you have plus 4 e to the negative 5s, e to the negative 5, sorry, this is e to the negative 5s, okay, so plus 4 over s e to the negative 5s. So we have 4, so this is 6 over s e to the negative 5s, okay, and then minus 2 over s. Okay, so you will observe that you get the same, you get the same answer. Okay.